All right, in this video, we're going to go ahead and give a couple more examples of determining molecular polarity. And these are the molecules we've been following through our lecture series. So we have looked at them in 2 dimensions. So here's our first one, CH2O, and we've converted it into 3 dimensions. We know this is a trigonal planar geometry around the carbon. And now let's determine if it is overall polar or nonpolar. So in this case, I'm going to use my handy dandy electronegativity chart that I've memorized already, but you have not. So it's up here. And I can see my oxygen is 3.5 and my carbon is 2.5. So I'm using that chart to inform this part of the process. So I'm going to write that down here. My carbon is 2.5, my oxygen is 3.5, and my hydrogens are each 2.1. And now I'm going to look at the differences between them. So my electronegativity difference between my oxygen and my carbon bond is going to be 3.5 minus 2.5. So that's 1.0. Now that's greater than 0.4, so this one's going to be polar. Now I'm going to look at the electronegativity difference between the carbon and hydrogen bonds. And there's 2 of these, and they're going to be the same, right? It's the same value, so I can just calculate it the one time. The carbon's 2.5, and the hydrogen is 2.1. That's 0.4. So that falls in the range of nonpolar, 0 to 0.4. So this one's actually going to be nonpolar. So I'm going to only identify the polar bond in my molecule. I'm going to do this in a different color. So I can do this with the delta plus on the carbon and the delta minus on the oxygen to show partial positive charge on carbon and partial negative charge on oxygen. Or I could do a little dipole arrow as well. And now I've identified my polar bonds in 3 dimensions. And now I can look at it and go like, is it overall polar or nonpolar? And looking at it, I don't have all polar bonds, right? I only have 1. And so there's no symmetry of polar bonds around the central atom. So I don't have to worry about it being one of those it's polar but nonpolar situations. So because half of this molecule has an uneven distribution and the other half kind of is sharing evenly, I'll have an uneven distribution overall. And so this will be a polar molecule. If I wanted to create a large dipole moment for the molecule, I would do something like this. Let's look at our other example that we've been working on. So this one is methanol, and we converted it from a 2D structure to a 3D structure already. All right, so here's our 3D structure. We've got that tetrahedral carbon and that bent oxygen, but they all have about the same bond angle of about 105 to 109. So looking at this, I'm going to go through, now that I have a 3D picture, and label my electronegativities. I've got 2.1 for each of these hydrogens. I've got 3.5 for oxygen and 2.5 for carbon. So I'm going to look at these bonds individually. So let's start with the electronegativity difference of the carbon-oxygen bond. That is, again, 3.5 minus 2.5 of 1.0. This is polar. And so I'm going to go ahead and add in that I have a dipole moment right here, where my carbon is partially positive and my oxygen's partially negative. And I have 1 polar bond there. Now let's look at the difference between that oxygen and that hydrogen. That'll be 3.5 for the electronegativity of the oxygen minus the 2.1 for the hydrogen. That's going to give me a value of 1.4. So that's going to be polar too, just like in the water that we looked at. So I have a partial positive charge on the hydrogen and a partial negative charge on the oxygen. I could also draw an arrow along the bond to show that, with the positive end at the hydrogen pointing at the oxygen. All right, one last type. The rest of the bonds, all 3 of them, are carbon and hydrogen. So that's the 2.5 minus 2.1 for the hydrogen. That's 0.4. That's nonpolar. So I won't write anything on them to indicate that they're nonpolar. And I won't put a dipole arrow because they're nonpolar. So now I can look at this molecule overall and say, huh, is it polar, nonpolar? I have polar bonds. They aren't perfectly symmetrical because they're around a central atom that has lone pairs. And so there's an unevenness in this overall molecule. It has a dipole moment that kind of goes this direction. And so this is going to be polar, even though half my molecule is nonpolar. And actually, that makes it even more so. I've got like all these nonpolar bonds and then polar bonds. That's a clear unevenness within the molecule.